Hey guys, before I get into doing an AM radio alignment using an RF generator and a VTVM, I wanted to touch on a few more topics about doing a visual alignment with a sweep generator and a scope. There's a couple things I forgot to mention. One is the use of markers, and two is the use of a demodulation probe. So here's a simple setup I have. One is my swept RF generator, and I'm going to use this for a marker generator. More on that in a bit. First, to recap a little, a normal RF generator puts out a sine wave of a fixed frequency. So in this case, I got about a 1 megahertz sine wave. Using a setup like this, you could inject this signal into your radio, and you could use a VTVM and measure the output of the AM detector, and you could find out at 1 megahertz what's the output I get. And then you could do it at various frequencies. And doing that, you could build up a plot like this. This happens to be for a Shure microphone, and along here they have plotted frequency, and here is the response. So that's really the goal when you do a visual alignment, is to find out at various frequencies what does your radio produce. More specifically, you're going to be aligning the IF transformers, which for the radio I'm going to be using is 455 kilohertz. So you would want to know what the frequency response is, say from 300 kilohertz to maybe 600. In other words, to get on either side of it and see exactly when you feed in that frequency, what is the output. So you could use a fixed frequency generator, just like I got here, and hook up your VTVM and do it at, say, 300 kilohertz, 310 kilohertz, 320 kilohertz, and so on and so on and so on, and plot the points on a graph and then connect the dots. Perfectly fine. The only problem is if you want to make adjustments to it every time you tweak the IF transformer, you have to go back and plot all those points again to see what change you made. So what a sweep generator does, it's really the equivalent of you taking your RF generator and just going like this, back and forth, back and forth. In fact, I've got an old sweep generator down here, I'll pull out one of these days, that literally has a motor attached to the tuning capacitor, and it rotates this dial around to produce the sweep frequency. And as you can see on the scope, you get that swept frequency. Now, to make your life a little bit easier on this device, it's set up so you can put it on 455 swept, and it will do that sweep for you automatically. You can see it kind of makes my scope freak out here as it's trying to lock on that and figure out the frequency, which is jumping all over the place, because what it's doing is it's making the sine wave go between those frequencies really, really fast. If I back up the scope even more, you'll see that it's an auto scale. And as you can see, it's really hard for a scope to lock on this because the frequency is constantly changing and it's modulating and so on. So typically these sweep generators will either have a sync output that you connect to the external trigger on your scope, or you can synchronize to the AC line. Because typically the sweep generators sweep the frequency at 60 Hertz, which is derived right from the AC line, and most scopes can sync to line, which will get these locked in. Furthermore, most sweep generators have what they call a blanking interval, which puts a blank. So it sweeps from one frequency to the other. So here's all those sine waves that were, wobbling back and forth. Get off one. So, but what I'm doing here, I'm decreasing the time base. So here we're looking at 2 microseconds per division. I'm going to drop this down and down and down and down. In other words, I'm making the scope sweep slower and slower. So the sine waves are getting compressed more and more and more, until now I'm looking at 2 milliseconds per division, so that's roughly about 8 milliseconds from there to there. So inside here are hundreds and hundreds of sine wave cycles going blah, 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 blah. And then there's a blank. The reason they put this blanking in there is to make it a little bit easier for your scope to figure out what's going on and to lock into that signal and give you a stable picture. Ideally you'll have a scope that has a delay on it, so you can lock to the line, and then you can use this control to scooch it over so you can see the whole thing and fill up as much of the screen as possible. So in this case, all I'm doing is the sweep generator is going right to my scope. There's no radio in between or any device I'm analyzing. So you're going to get the same amplitude all the way across the board. Now here's where the demodulator probe comes in. That's not very useful to look at. You can't get any accurate values out of that because there's all kinds of oscillations going on in there. So you get two choices. If you're working on an AM radio, you can connect your scope to the output of the AM detector, which is essentially a rectifier, just like when you rectify the AC line voltage onto the wall, turn it DC to power your radio. A detector takes this and rectifies it. The other choice is to use a special probe like this, which is called a demodulator probe. What's inside of this is a diode and probably a resistor and a filter capacitor, just like an AM detector on a radio. When you hook this up, it will transform it into that, what you see on the bottom there. This is a dual trace scope, so I have one going to still showing those swept sine waves, and then the second one is the output. And because there's no device in between, no filters, no IF transformers, this bottom trace, if your sweep generator is working properly, should be a straight line, which means every frequency is coming through at the same amplitude. It's just a straight piece of wire. There's no filtering going on whatsoever. Now, as for what markers are, so inside of here we're going from probably somewhere around 400 kilohertz to 550, something like that. But if I want to get an accurate chart like this, I want to know right here what's the frequency, right here what's the frequency. I don't know. That's what you need a marker for. So if you have a sweep generator like this, this whole right side is just to generate those markers. A marker is a blip. You literally get a little blip right there, and you can read off the dial, and the dial will say, like, say it's on 2 here, so maybe 2 megahertz, and if you see a blip right about here, you know at this point you're feeding 2 megahertz into your device, and then you can see how it responds to 2 megahertz. Another way to do it is simply use a separate standalone RF signal generator and feed that in through a capacitor or a similar device. You don't want to directly short the two RF generator outputs together. And the two signals will mix, and you'll see a peak where the two frequencies are the same because it'll be like additive interference. You ever took physics when you learned about when water waves hit each other and you get peaks and troughs and all that? Well, when the two frequencies, in other words the swept frequency equals the marker frequency, you get a boost in the amplitude and you get a blip on the screen. Or on the scope, I should say. And they must have already had that in mind. I never noticed it before on this, but on this RF generator, you can see at 455 they put a special mark on there. So somewhere, I know, in between here and here, it's 455. Well, if I put this directly on 455, and let's see, hook everything up, I should see a blip on my scope at 455. Okay, I had to wait for this to warm up a little bit. And now, you see this crazy squiggle there? That is what they call a marker. So I know that right there is 455 kilohertz. If I want to know what the frequency is at other portions, I just rotate the dial on my marker generator and you'll see that tick go back and forth. So if I want to know what the frequency is right about there, I'll look over on my dial here and I see, oh, it's around 480 kilohertz. Now when you use these, you want to be a little careful with the amplitude. If you feed a really strong marker signal in, it's going to really swamp out your sweep generator. So keep it as small or as low level as possible. You can still see that marker, which they actually call a pip. This squiggly thing there. So between the demodulator probe and the marker, I can now figure out exactly what's going on here. So when I want to peak my IF transformer for 455 kilohertz, set this on 455, feed this signal into the IF transformer, and make it peak where you see the squiggle. Now there is one other way to get markers into this device, which is to use this crystal socket here. Unfortunately, I do not have a 555 kilohertz crystal, but the idea is you would take one, pop it in, and it would make the same type of squiggle just like I got with that guy. This is a 100 kilohertz crystal, by the way. Now, by way of an example of what the response curve might look like, here is a crystal lattice filter out of an old Collins receiver. On the top here, I've got my swept input, and on the bottom here is the actual response of the filter. So I see it's got a peak response right about there. So that's the kind of thing you're trying to look at with the detector probe. Now you don't have to go out and buy a specialized demodulation probe. You can easily make your own, and there are a number that came for old VTVMs, and sometimes they call them broadband detectors or detector probes. Simply a diode and then a pi filter resistor, a couple capacitors, just like an AM detector in a radio. Likewise, they show one here being used with the sweep generator. If you just Google demod probe, demodulation probe, detector probe, I'm sure you can find some schematics online. Just remember that this diode, you should use germanium type, like a 1N34, I think, because you want one that's very sensitive to low-level signals and will work better at higher frequencies. So that's all I've got on sweep generators. If you have any more questions, please let me know, and I'd be happy to do some more videos. In the meantime, I am going to move on to finally do alignment with VTVM.